So the motivation behind this work is that there has been an increasing number of robots in construction domain, especially mobile robots, which are now widely deployed in actual job sites for many potential applications, such as site progress monitoring, safety surveillance, etc. So for these robots, mobility is the core essential functions to complete their task. So these days, they are expected to have more autonomy so that they can perceive and navigate through the environment without any help from the humans. So when we think of these autonomous robots being deployed on sites, moving and working near human workers, we have to think about how we would affect the current workplace. So we need to make sure that it does not bring any additional safety risk, such as collisions. But moreover, there are other more subtle consequences as well. So if the robot's behavior are not aligned with people's expectations, for example, they can negatively impact the workers' work experience, maybe by blocking their path or interfering with their works. So this can cause inefficiencies, and eventually it would make the robots to lose their trust or acceptance from the workers. So to avoid this, robots deployed in human populated environments like constructions needs to be not only safe, but also socially compliant, following the social norms or conventions. So as social norm contains multidimensional aspects, one may ask, so in the context of constructions, which aspect of social norm should we consider the most? And in this study, we claim that the most critical element of social norm in construction is to maintain an appropriate distance or separation from people, because construction environment often tends to be highly cluttered and dynamically changing. Various activities are usually operated in very close proximity, causing many risks. So when autonomous robots are deployed, there will be more direct and indirect risk from sharing these workspaces. So any violation into personal spaces can cause inefficiencies and even fatal accidents at the worst. So in this work, we explore the various social navigation strategies, which refers to the robot motion planning that accounts for social norms and conventions. However, we learned that the most existing work considered all the pedestrians as equal agents without considering the fact that in reality, individuals can have their own idea of personal spaces based on their own situations. And we believe that this is more true for construction workers who are usually situated in various work contexts. So robots should understand such differences and give priority to those who have greater needs of personal spaces, as illustrated in these photos. So the goal of this research is to propose RL-based social navigation algorithm, which incorporate work context-related proximity needs of different workers, so that the robot agents can learn how to plan their future trajectories to their final destination while maintaining an appropriate distance from different pedestrian workers. So as the first step, we define different proximity needs of workers, which were determined by their work-related activities. So we provided 3 different work zone distance for normal pedestrian workers, load-carrying pedestrian workers, and finally inactivity workers, respectively. So the smaller worker zone indicates that there are less activity disturbance or safety risk compared to the larger work zone groups. Then we incorporated these pre-identified proximity requirements into the existing social navigation algorithm, And we formulated this problem as a sequential problem within our framework where the robot agent interacts with the environment, observes the state of the other human workers, and then make a sequence of decisions to maximize the expected return. And we use two state-of-the-art RL algorithms for our models. So the first one is DQN, which is a value-based RL method. And the other one is TRPO, which is policy-based RL method. And for detailed explanation of these algorithms, please refer to our paper. For our experiments, we used a simulation environment called RVO2, which is basically a real-time multi-agent simulation library that generates various pedestrian movement based on the reciprocal collision avoidance mechanism. So here is the summary of our experiments. The resulting low density setting showed that while our proposed model performed similar overall navigation performance, it still showed significant improvement in terms of social conformity, having lower violation rate as well as larger separation distance compared to the baseline models. The results in high density setting also showed a similar trend in general. However, the overall performance in high density were decreased based on the lower density setting, having higher number of failures and violation cases. So we suggest that it would be more challenging to learn and adhere to proxemic needs in high density situations. And we may need interactive and corporate planner to handle such cases instead of the current reactive planner. So to conclude, our preliminary study demonstrated the potentials of our proposed context-appropriate social navigations in making the robot more aware of and responsive to varying types of pedestrian workers with different proxemic needs. And we believe that these findings can contribute to building future construction mobile robots with more social intelligence, which can allow the robots capable of understanding the work context of constructions and adapting to appropriate behaviors accordingly. However, our work has several limitations. So the first limitation is that all of our experiments were performed in very simple simulation environments, excluding any geometric layouts or obstacles. So our model may not work well in the real-world settings. So to avoid this in the future work, we will include both stationary and moving obstacles in addition to spatial layouts so that it can better represent the characteristics of construction job sites. And secondly, our robot agents are not capable of inferring the proxemic needs of workers. Instead, we provided the predetermined value of proxemic requirements. However, it's very unlikely that this value will be fixed or this information will be provided to robots in the real scenario. So in our future study, we'll make our robot agents to learn how to infer this dynamic social spatial requirements by leveraging the data collected from robot sensors. Thank you for listening to my presentation, and if you have any questions, please let me know.